Hello, everyone. First of all, I would like to apologize about my voice. I hope it's going to last me till the end of our presentation. Uh, my name is Michal Fartas. I'm a senior DevOps at Egnyte. I've been working with Kubernetes for last 3 years. And today, we're going to talk about autoscaling. But first, how about a show of hands? Who is using Kubernetes? Okay, and who is using autoscaling in his Kubernetes cluster? Okay, good. So uh, this is our agenda. We will focus a bit on cluster autoscaling, as much as it is pretty simple at the start, but it's also going to be valuable for other people that's not as familiar with Kubernetes as the ones who are using it. But we will also touch on some aspects that might be surprised even for those people who are experienced with Kubernetes, because often this autoscaling can leave you with a specific sense of comfortableness in a way that you think that everything is being done for you, while actually there's a lot of catches hidden in it. So we're going to talk about impact of autoscaling on networking, on the load balancing, on high availability, and then in the end we're going to touch on horizontal pod autoscaler and good practices for the application. If there is time, we might talk about autoscaling patterns for the application. So let's get on with it. First of all, kind of to clear up any kind of confusion, differences, we have pods, deployments. Pod is a set of containers deployed on a node. Pod is assigned, created to a node, and that's for the whole life cycle of it. Deployment is a specification of pods, number of replicas, its configuration. Node is a server in a cluster. Node pool defines the set of servers. And our heroes of these presentations are cluster autoscaler and scheduler. Cluster autoscaler defines how the whole cluster behaves, which nodes to add, which to remove, and so on. And scheduler assigns pods to the specific nodes. So first of all, to understand how autoscaling in Kubernetes works, we need to first understand scheduler. Scheduler bases its work on two core resources, which are CPU cores and memory. And also you can define constraints like on which nodes it should run, what kind of affinity to which nodes, to which pods it has, and so on. So each node defines some capacity. Usually you can find for a provider a definition of, for each machine type, of capacity and how much is allocatable. Always remember that even if you have like 4-core machine, it's not always allocatable all 4 cores, because Kubernetes on its own is also using some resources. So always check with your provider. Here's an example from Google Kubernetes engine. And pod defines its requests and limit. Request specifies how much resources it needs to start up, and limits is how much it will use at max. So you can see here an example definition of pod resources, and this information is being used by scheduler to define where it can assign a pod. And underneath you will see here description of node resources, so you can see a list of pods for a node and how much resources it's using, and kind of a definition of everything for the node. So if we have that now cleared up, let's talk about how scheduler actually works in action. So we have here a scenario with 2 Kubernetes nodes. Node 1 has 2 pods, node 2 has 1 pod. And now we create a new deployment. Let's call it deployment Z. And deployment Z requires 1 replica of pod Z. So it makes requests, and scheduler takes action and assigns new pod Z, to a node where there is a space. So that's kind of straightforward. First tutorial in Kubernetes, that's how it works. So what if deployment Z now requires 2 replicas? what will happen is scheduler will detect that it has insufficient resources on available nodes. And pod is going to get stuck in the pending state. And now autoscaler appears. Cluster autoscaler can detect how many pods are being stuck in a pending state, how much resources they need, and how much does it need to allocate. So quickly, it creates a new node, and now scheduler can easily assign the pod to the newly created node. So let's now see how it works other way around. Now we delete deployment Y. So scheduler decides to remove both Y pods, and we end up in this state. So what happens now is that scheduler detects, together with cluster autoscaler, that the cluster is underutilized. And now it can make decision which pod to evict and how to manage kind of the whole application, the whole set of pods on the cluster to allow for you the best usage of resources. So what's going to happen is pod Z2 is going to get a message about eviction, and cluster autoscaler will disable scheduling on the node 3 so that no new pods are going to be assigned. And after graceful termination period, after everything is removed, new pod is going to be created on a different node because scheduler needs to maintain number of replicas, and node 3 is going to be removed. So in a nutshell, this was how cluster upscaling, downscaling works in Kubernetes. That's basically kind of capacity autoscaling. So let's move to the most interesting part. How this autoscaling can impact your day-to-day operation, the way how you deploy your application. So first, let's define kind of our practical definition of high availability. In my opinion, it's a combination of replication and fault tolerance. As you've seen before, replication in Kubernetes, it's easy. You just change a number, set a number of replicas, and it's being deployed. So let's focus on fault tolerance. First one, the kind of easiest to reach is node failure. So let's go back to our previous scenario when we have two nodes. And what happens if node 2 dies? Well, we had both pods Z on the node 2, and with single node failure, we get the whole deployment Z service down. So how to deal with that? It's pretty simple. You have something called pod anti-affinity in Kubernetes. Basically, with this configuration, you can tell scheduler to try to avoid scheduling two types, the same pods on the same node, same type of pods. So this way, you can match the labels and say that the same type, the pods that match the same labels won't be deployed on the same host. But this is also a soft requirement, so if it's kind of fitting capacity, pods can be collocated, but scheduler will try the best to distribute your pods among your cluster. So what would happen with that configuration is actually when the situation where node 3 was being disabled and deleted, the pod Z3 would be assigned to node 1 instead of node 2. And now let's go to an even more interesting topic, eviction tolerance. So the question here, who here is familiar with a term pod disruption budget? Okay. So previously, many of you raised your hand that you use cluster autoscaling, you use Kubernetes, but now less than half of you raised your hand. And actually, that's something I observed for a while now, that this is a nice piece of critical configuration that gets dismissed all the time. So let's have this type of situation where you have 4 nodes. On each, there is a pod deployed. And again, we see that cluster is underutilized. But this time, we have the pod anti-affinity to have the pods distributed among nodes. So it's kind of, we think it's safe. So what can actually happen in this scenario is that scheduler can decide to evict both pod Z1 and pod Z2 at the same time, and effectively shutting down your service, even though you have configured the distribution among many nodes. Why? Because you didn't define pod disruption budget. This is actually the only piece of configuration that will make sure that during stuff like downscaling, like node upgrade, and so on, that the scheduler is going to try the best to have your service, your pods, to provide minimal availability. Pod disruption budget can be specified using either max unavailable or minimum available. It can be specified using numbers or percentage. So this configuration here, this example, will make sure that the eviction will occur one pod at a time for this service. Next, cluster autoscaling and networking. To understand how the autoscaling affects networking first, let's discuss how actual load balancing, how networking works in Kubernetes. So this here is a typical example of service deployed with type load balancer. So you have pod C deployed in node 2 and node 3, and load balancer in front of a cluster is actually routing traffic to any of the nodes in the cluster. And only after reaching the node, the request is being routed using kube proxy to a different node. Actually, how it works right now with round-robin load balancing in the services, you can actually, for example, make requests to node 3, which has a pod Z, but the request would be routed anyway to node 2. So let's talk about this case. So we have a user that makes a connection. Connection goes to node 1 and reaches pod Z1 on node 2. Right? We have everything set up as it should be for deployment Z. We have anti-affinity, we have pod disruption budget. It's nice, everything is working. And let's say we have a long-running connection, like, for example, WebSockets. So now wild autoscaler appears. And what happens if the cluster autoscaler decides to delete node 1? Your connection gets interrupted. So even though you've configured all you can for deployment Z to have the uptime to make sure that everything works fine, even though it is from within the cluster, you'll actually get interrupted connection from the customer. So how to deal with that? Solution is use external traffic policy local. This changes the behavior of a load balancer in front of your cluster. So what it does is each node now will only route requests to the service Z only to the pods on the node. And also it will expose a health check. That is going to display, does this node have those pods? So now, how it will work is that load balancer checks the health check on each node and routes requests only to node 2 and node 3. So basically now we've reached the same level of availability as we wanted with our deployment configuration. So that's kind of covers most of the configuration for high availability and good networking. Well, it doesn't really, because actually, let's look at this case, right? We have 4 nodes, again, and external traffic policy local that routes requests to node 1 and node 2. And we have deployment Z in version 1, right? So now we want to update the configuration of deployment Z. So 2 new pods gets deployed, and because of our previously configured pod anti-affinity, they're going to be allocated to node 3 and node 4. New version starts, old version gets terminated, and what happens now? And now we have downtime. Why? Because load balancer actually has a refresh interval on checking the health checks. And even though you also configured everything to work as it should, you will get some delay. So the story continues. Remember this the configuration for Antiaffinity? Well, say hello to Big Daddy. It looks now like this. So what we've done here is combine Antiaffinity and Pot Affinity. So we still have the previous configuration where we have Antiaffinity for the same same type of pods from the same deployment, right? We want to distribute them on a different node. But this time we also add additional label, which is called here build revision. And this time we want to specify that not only of the same deployment, pods of the same deployment, but also of the same version want to be distributed. But later on, we also add pod affinity that makes the configuration such as the new version wants to be co-located on the same servers that the old version were deployed. So if we, if we visualize that, this time the second version pod of deployment Z will be deployed on will try to be deployed on separate nodes for itself, but on the same nodes as the old version was deployed. With that, you avoid changing the health check, you avoid mixing it up. Probably some of you already seen some potential issues with this configuration. You can reach certain edge cases if you have you run out of capacity and so on. You can probably tune it also with pod priority and so on, but that's kind of completely separate topic altogether. But actually, there is a hope for the future. GKE introduced some time ago something called container native load balancing. The idea here is instead of using load balancer that addresses the nodes, why don't load balancer address the pods directly? This is leveraging the LSIP and native support for VPC in GKE. And with that, the pods IPs are accessible to the load balancer directly through the network. It doesn't have to go through kubeproxy and so on. Unfortunately, this is still in beta, so we're still evaluating if it's going to be the most reliable solution. But the way it looks is now load balancer can address the pods directly, and we also avoid the issue with health checks, because instead of using health checks, the ingress controller in the cluster directly updates load balancer with list of new IPs. So every time something changes in a cluster, load balancer is first to know. So you've got like both benefits of direct access and the safety. But unfortunately, this solution is kind of provider specific, so. Now, let's move to the second part, pods autoscaling. So, to achieve pods autoscaling, so basically our ultimate goal for application to be autoscaled, you need to use horizontal pod autoscaler. This is actually a bit kind of, I would say, controversial piece of code in Kubernetes, because right now we actually have 3 different versions of horizontal pod autoscaler specification. You have V1, V2, Beta 1, V2, Beta 2, and each one has a different configuration, different implementation is available on different version of Kubernetes. So I'm going to touch broadly on it, and if you want to implement it on your own cluster, make sure to check which version do you have available and which version of documentation you're actually reading, because it can become tricky. So basically, horizontal pod autoscaler is another object in Kubernetes that controls how many replicas do you have in a deployment. So it checks a defined metric. It can be internal, external type of metric, and evaluates the value that you provide, a threshold of a metric. And from that, it calculates the desired number of replicas and applies specific policies such as minimum number of replicas, maximum number of replicas, and also it applies additional upscale, downscale delay. So to prevent thrashing, you've got some delay between scaling periods. Type of metrics. The original type of metrics that were being used, and actually for V1 version, I think it's only available to have CPU-based auto-scaling, was resources. So basically, the stuff that Kubernetes, that the scheduler operates on. So you've got CPU utilization and memory utilization. The second type of metric that was introduced was pod metrics. And pod metrics basically rely on that each pod expose its own metrics, and then metrics server can gather the metric from all the pods and apply, for example, the desired average value for your auto-scaling. So good examples of that are requests per second, connected clients, so each pod can say what its usage is. And finally, you have also an external type of metric. So it could be like a backlog on a message queue, and queries per second on the load balancer, and so on and so on. So for the final stuff, let's run over some good practices and tips for a kind of auto-scaled application. Obviously, for the container itself, the critical parts are quick startup and lightweight containers. If you want to auto-scale fast, your application needs to start fast. And also, if image is light, it's going to be downloaded quickly, and so on and so on. Second part is fault tolerance. Remember that not only your application is going to be upscaled, it's also going to be downscaled. So each container can be killed at any time. So remember to add as much kind of retransmission, reruns as possible, and also kind of connection drying and so on. And obviously stateless, but I guess that's kind of a standard right now. For the infrastructure itself, often some opportunities and traps. From the opportunities, I would recommend using cheap and kind of unstable, let's say, VMs. A good example of that is in GCE preemptible VMs. There are VMs that live at most 24 hours, and actually Google can kill them at any time within that 24 hours, but they're 80% cheaper than normal VMs. And if your application is quick to start, stateless, and so on, it doesn't really matter to you because the new VMs are getting provisioned constantly. They're getting removed, they're getting created, you get autoscale, downscale, and your infrastructure actually can get very, very cheap. And especially it's useful for stuff that uses large amount of, for example, a CPU that requires calculations and so on. But as I said, other than the opportunities, you also have potential traps. What's often overlooked with auto-scaling is the impact it has on secondary service. Because when you auto-scale a service, first thing you think about are bottlenecks like database, cache, and so on. But people often forgot about impact on monitoring, on logging. You have to prepare your infrastructure to be handled the spikes in your processing. Also stuff like image registry, kubedns. There are often like traps that can surprise you, can jump out at the least expected moment. And also tip, watch out for silent failures. If you have a large scale, a lot of auto-scaling, you can have containers that start up quickly, do their work, do the load, and downscale. At that time, you can often miss the cases where the application is not safe to run for a long time, and then suddenly, if you have a prolonged load, you have like a few hundred containers running all the time, and suddenly you have new issues that you weren't expecting before. So be always careful to monitor those failures. So, any questions? I think I was asked to reserve 5 minutes for questions, so. Responsible for questions.
Hello. Then just run away somewhere. And there are no questions, actually.
Okay.
Or we have something from the crowd.
What about combining cluster autoscaling and pod autoscaling? What are your experiences with that?
Well, if cluster autoscaling works properly, if everything is configured, it becomes transparent. So basically, horizontal pod autoscaler changes number of replicas, and it triggers cluster autoscaling automatically, and you don't really need to worry about it.
Okay, and new fancy stuff. Have you tested vertical pod autoscaler?
No, I mean, I get the idea of vertical pod autoscaler, but honestly, I'm a bit against it. I mean, I understand the use cases for stuff like, databases being deployed in Kubernetes and so on, but no, I still haven't had the opportunity. I deal mostly in kind of cases with many containers, large scale in that regard, so I'm much more invested in actually horizontal pod autoscaling. But yeah, actually, other than vertical pod autoscaler, we've been talk about new stuff like node auto provisioning. So this is a new concept where scheduler and autoscaler check the resources that you require, which pods you want to assign, and actually the autoscaler defines the type of VM that you need. So instead of defining in a node pool the size of a VM, it can decide for you, create a new node pool, and manage it accordingly. But still, it's, I think, in beta. So if there are no more questions, I think we have 3 minutes, so I can jump into the bonus topics, actually. Also, kind of, I mentioned if you have time, go check out our Facebook group, Kubernetes User Group Poznań. And let's jump into the bonus topic, autoscaling profiles. So let's discuss quickly 3 most common use cases for autoscaling. So the one that you often will see on tutorials in Kubernetes, so like Frontend Traffic. Second is event stream, and third, batch processing. Each one is different on its own, so I think they're a pretty nice case to discuss for different types of autoscaling. So first of all, front-end traffic. Obviously, it's like requests from external customers. You don't know how much load it's going to generate. You don't know how much customers are going to jump in today and so on, but it's at the same time, it's critical. You need to respond fast. Latency is the most important aspect. So my recommendation, remember about minimal capacity. Don't be too cheap, because there is often this notion that I can downscale to 1 replica and so on. I can save as much resources. Remember that autoscaling is kind of a periodical job. It has some limits and has some delays. So for critical services like this, remember to ensure minimal capacity and then kind of build from that. Actually, this type of autoscaling works best if you have a large-scale application, if you have millions of customers, coming into your service daily, all day long. That's the cases where you can actually, change the capacity by a small margin, but still kind of take advantage of it. Also, kind of metrics to use. The most common one are obviously CPU utilization, query per second, connected clients. It depends on your application. It depends on how you use it. Second, event stream. Obviously, to deal with cases, the issues from HTTP services, people often moved their application to use message queues, to use events, and kind of how it works basically is you have stable stream of requests, usually predictable execution time, especially kind of microservices. So for this, to autoscale, the best metrics are actually throughput and backlog size. Remember to ensure that the throughput on both ends of a queue are as balanced as possible, because that's actually what you want to reach, right? You don't want to overcommit. You don't want for latency to increase, but also do a proper research and find out how much is an acceptable lag for your event stream, because adding some acceptable lag to your application, to your kind of auto-scaling profile, can actually save you a lot of money and prevent thrashing, prevent sudden upscales and so on. And finally, you have batch processing, which is a bit similar and different at the same time from event stream, because where in event stream you get a constant flow, and batch processing you can get millions of messages to the queue at the same time. So it will create a huge spike in the backlog, and requests can often vary in processing time, because it's often stuff like business analytics, some machine learning, and so on. So try to process everything at the same time. Try to use your full performance, because if you get a batch, the best option is to upscale to the max, process everything, and downscale to 0. So for that case, you want to balance the metrics, right? The best option that I've seen until now is balancing between backlog size and backlog age, because if you use only one of those metrics, you will face one of the issues mentioned here. So if you use backlog size, you will scale up fast, but then you're going to slow down as you process the messages from the queue. If you use backlog age, it will cause the application to slowly ramp up. With horizontal pod autoscaler, you can actually use 2 metrics at the same time, and Kubernetes will choose the one that defines a larger number of replicas. So with that, you can define an ATA, calculate your metric, and achieve the proper autoscaling profile. And that's it. Thank you.